All right. Well, first off, thank everybody. Thank you very much for the invitation to come here and present some of this work. It's going to be quite a bit different from a lot of the things we looked at, or at least I thought it was going to be, but we'll see that some of the stories that Pedro just told us about, we're going to hear some similar stories here as well. My focus here will be to understand really what is the strength of the lithosphere on various planets. And so we'll be talking about strength profiles. So we're going down in scale from global core things to mantle, upper mantle. Now I'm going to be in the lithosphere part, the uppermost mantle and the crust. See how its strength should vary with depth. And the wrinkle that we've been working on with my colleagues Frédéric Guédan and Jacques Pressigo over the last few years is to add also not just a depth dependence, but also a strain dependence to this strength profile. Not look at them as static images, but as an object that's going to evolve over time. And we will discuss a little bit what would be the possible implications of this change in the way that of the resistance of the lithosphere with strain. What are its implications for planetary tectonics? The overarching goal here, and I think for probably half of the audience, is to understand why we have plate tectonics on Earth and only on Earth. This is Earth and Venus. We are downgraded the topography of the Earth to be like what we have as the data sets on Venus. And at this scale, as Sue told us yesterday, we see very clearly the difference in the character of topography. Of course, what we see mostly is the difference between continental and oceanic crust, but you have these linear mountain belts which are clearly developed even at that resolution. You really don't have much equivalent there on Venus. So there's been a lot of debates about what really, or a lot of ideas rather, of what could cause the difference between the global tectonic styles of these two planets. One of the ideas has to do with the strength of the lithosphere. I'm going to push this idea as far as I can, and I'll see that I'm probably going to be failing short of the goal of explaining those differences eventually, and we're going to have to think of other causes. But before I go there, I want to reinforce the fact that when we say plate tectonics, or there's no plate tectonics on Venus, does not mean there is no tectonics on Venus. Even on Earth, the word tectonics is much older than the concept of plate tectonics, and that is also something we have to remember on the other planets. And some aspects of the tectonics of other planets, I'm talking Venus in particular, really looks like what we see on Earth in some environments. And that should give us some clue about what aspects of Earth insight can be carried over to other planets and what cannot. So for example, if we're looking at extension, for example, okay, this is the main Ethiopian rift in East Africa on Earth. That's on Earth, right? Basically, the quintessential continental rift environment, we can see a fairly linear object with a width there of a few tens of kilometers with a nice fault, etc. And if you're looking at the Van Casimir region and Beta Regio on Venus, you have also similar lengths, similar widths, and also a bunch of faulting and things like this. So in fact, morphologically speaking, those two rifts look extremely similar. And a lot of people have done comparison in terms of, fault offsets and things like this. And essentially, whatever we think is going on in here actually is probably also applicable here on Venus. And this is going to be the case for extension. Shortening is quite different. Sue mentioned to us yesterday the potential of some limited subduction zone in various places. I want to talk about something else. A lot of the contraction we see on Venus is these ridges, wrinkle ridges that are covering regional planes, and each one of them is a fairly small object, but the plane of a broad distance are essentially covered within a uniform density of this type of objects. In this case, the deformation has no localized, no high strain, a region which has much higher strain than anywhere else. The deformation is essentially diffused throughout the plane, although everywhere you have these small faults. That's typically not how shortening is accommodating on Earth. Usually you will have a much more localized mountain belt or something like this. This is maybe one of the broadest deformation zone we have. It's in South America, where you have basically the Andes, and you have more uplifts, more zones of contraction going off several hundred kilometers away from there. So we're getting the same scale as what we have here. Oh yeah, I should have mentioned, those maps are always drawn at the same scale so that we can compare comparable things. But clearly you have bigger, more widely spaced uplifts for still more localized deformation in these regions than in there. Already one thing you may have noticed is that all my examples there of things that look as Venus-like as possible on Earth are always in the continent. It's maybe something to keep in mind later on. So what we're going to do is to try to think about how strength varies with depth and with strain in planetary lithosphere, and basically what could be explaining the difference in behavior between most Earth, not this Earth, but most Earth and Venus, and Mars and this type of places. First, I do want to give you a little bit of a review about what we mean by strength envelope and how they are constructed. So it is taken from a recent textbook by J. Mellish, the cartoons of what a strength envelope is. And you can see basically it's a profile drawn of strength of some measure, this could be done in different ways, but essentially some measure about the stress that you need to put to deform a material and how it changes its depth. And you can see from this kind of classical view of strength envelopes, you will have regions where you have a fairly thin region of high strength, with planets where you have a thick region of high strength, etc. And certainly I have nothing much to say about this against this type of approach. It's perfectly fine. I think we have to go one step further, though, as I'll show in a little bit. The way these are constructed is comparing the stress that is needed to deform according to different deformation regimes. So near the surface, you have brittle failure essentially producing cracks and faults, the stuff that makes that have some manifestation at the surface that we can see, for example, in the image that I showed before. And in this case, the brittle failure, the stress required for brittle failure increases with pressure, so it increases with depth, and that is responsible for those straight lines in those strength envelope, the shallower part of it. At depth, you have more ductile creep, and that is going to be responsible for this more curved version part of the strength envelope. And creep depends on temperature as well as the imposed strain rate. All of these envelopes have been drawn for a specific strain rate, and I totally forget which one, but it doesn't really matter. I should also say that a lot of people who do numerical modeling and of geodynamics also add typically a strength limit, which is fairly arbitrary, saying we don't fool ourselves that you have actually this very sharp high strength region. You probably have some limiting phenomenon here with actually very limited experimental evidence that this exists, but experimentally we also think that this does not exist. We just don't know what to do instead, so often people will just put a cutoff there. I will not mention it very much, just something that kind of already tells you that those strength envelopes are really just indications. They are not really the truth, they are not the final answer, they're just, guidelines. They've been used, in some extent already, to try to explain why Earth has plate tectonics and nowhere else. So there was a paper a few years ago by Craig and co-workers, and what they do is they've done numerical simulations. I think it's a Cartesian 2D box, which is not great, but whatever. And in their simulations, they report conditions for which they have an intact lithosphere and one where you have a failed and mobile lithosphere, which they interpret as plate tectonics. We could go on in that discussing this forever, but let's not go there. And there is a marked line on this plot between the two. The axis in here actually the driving force that is acting on the plate in their model, and here the depth of the brittle transition, basically the depth at which you have this peak there, the transition from the brittle to the ductile level here. And what they plotted is Mercury, Moon, and Mars, the smaller planets, the one for which we really don't have much evidence for plate tectonics, or none at all plots in the intact regime part of the diagram, which is great. Venus and Earth plot up there, and Earth is the only one which is totally failed on the failed regime, so it's the only one that should have plate tectonics, that the only one that does. Hallelujah, we solved it. Well, yeah, except that the reason why it plots up there is because they took the strength envelope, they arbitrarily decide, oh, actually it's weaker on the Earth than it is on Venus. So they kind of decided to say, okay, the strength envelope, this kind of, the brittle part, especially the straight line part, does not increase as fast with depth as it does it doesn't increase as fast on Earth, that it does on Venus. And therefore you have a shallower brittle ductile transition, and you have higher driving force, etc. So this arbitrary weakening is what makes those plots up there. Otherwise, they would be indifferentiable from what is on Venus. So the questions I will really be asking is, if that is the case, if we have weaker deformation zones on Earth than Venus, why is that so? What are the possible mechanisms that weaken plate boundaries and that weakens the lithosphere of the Earth and enable the formation of plate boundaries? If we can identify something that works on Earth, can we make the case it doesn't work on Venus? Because otherwise we don't have right to move the points from the Earth and not moving the points of Venus. Mars as well, we have to take into consideration, but certainly Venus is something we need to be very much worried about. And as we'll see that this is not so easy to do, then is the concept of a strength in this diagram really all that is needed? And I will try to argue eventually that maybe buoyancy, just like what Hans-Peter was telling us, could play a very big role. Anyway, So let's move on and try to identify the mechanism weakening plate boundary. First, the way they did it in here was to just look at the brittle envelope and say it is not as strong on a place like Earth than it is on Venus. And there's some actually good evidence that this probably is the case. So there's been a lot of studies on this topic. I'll just pick one which I like particularly, and it helps me later on in the presentation as well, by Cristiano Collettini and co-workers in 2009. And what they've done is that they essentially tested experimentally rocks that come from an exhumed fault, an old fault that is now currently, actually I forget where. Anyway, this is essentially an exposed fault. They took the material, tested it in the lab, and they found coefficient of friction in there that were of the order of 0.3 to 0.4, some numbers like this. They're not the only ones. In fact, people have done this with samples of the San Andreas fault as it's been cored at depth. They also found low strength, so we know that the fault material is fairly weak. Now, we always have to remember what are the reference. The textbook I'm going to tell you, and that's what's used for those brittle envelopes, that the coefficient of friction of rock is 0.6. They tell you that, and there's been a lot of evidence, a lot of experiments showing that, but when they take the actual fault, they got lower numbers. Why is that? Well, the thing is that faults do contain some minerals, like smectite, talc, and a little bit of chlorite in this case, and that's about the same stuff that we're seeing in San Andreas fault, that are intrinsically weaker than most standard silicates. So most studies have found high friction coefficient. When you look at this guy, you find lower coefficient of friction. But of course, you are not dominated by those minerals. You have a mixture of them. And what they've done in there, which I think is really insightful, they took their rocks there and they crushed them, make a sample out of these crushed rocks, and tested them again. And now, ta-da, they have high strength. So basically what happened is that the texture of the fault was actually important. By crushing them, they removed any structural information on the fault. So basically what you have is that if you have this, you must have in there some level of interconnection, formation of some level of a network of those weak minerals that essentially controls the strength of the fault. So basically what you have is you have to have a weak fault, you need to have the right type of mineral, and you must have that interconnection, which essentially requires that you have enough displacement, enough deformation to form this network. So on Earth, gosh, this thing has moved again, sorry about that. Focusing, no. Okay. On Earth, you will have basically the right type of mineral and the right type of environment to form this type of interconnected network, and maybe you don't do this on other planets. But there has to be something else happening on Earth, and here's why. The weakening from this brittle regime is just not enough. So numerical studies have shown that essentially you need a very low strength for the lithosphere of the order of just a few megapascals, and that is much lower still than what you can get by just decreasing the brittle strength. Another thing is, while this is a schematic diagram of the brittle ductile transition, you have the brittle material, you have the ductile one, and you have the transition in there. Earthquakes are thought to happen only in the brittle regime, and we know pretty much what is the depth of the earthquakes. And if you use flow laws from the lab and the brittle rheology from the lab, not the reduced one I just mentioned, but the kind of more classical one, you will have depth for that transition, which would be okay with the depth of earthquake. The problem is that if you reduce the coefficient of friction, look what's going to happen to this diagram, the transition goes to a greater depth. So if all that happens on the Earth is that you weaken the brittle regime, then in an active deformation zone, in a weak deformation zone, you should have deep earthquakes. Well, that's not what we observed. In fact, in San Andreas fault, there will be only, or Anatolian fault, or whichever one you find, earthquakes limited to 10, 12, something number like this of kilometers, which is relatively shallow. So what you need to do is to weaken the ductile part as well, so that now everything is weak and you are back to have the ductile transition on Earth compatible with the observations. So what we've been doing is to look at what happens in the ductile regime, in deforming rocks in this regime, and if we can make an argument to reduce the strength of the ductile part now from what it is if you just take the flow laws from the lab and apply them without any more thinking, and what probably is happening, at least on Earth. So I could spend, another half hour, which you don't want me to, but I would spend another half hour telling you exactly what we've done. So just jumping to conclusion, here's kind of a diagram of what we think happens in the San Andreas fault. So shallow depth, you have brittle regime, which makes the earthquake, kind of classic, weakens as I mentioned, but that's fine. Then you have a layer immediately below that where the ductile deformation gets to lower strength because you have, again, formation of some fabric, some interconnected network of some relatively weak mineral, ferrosilicates in this case. We couldn't find a way to weaken the lower crust, so it remains strained, at least in our view, and we'll see that there's actually some evidence for that. And the mantle also on the top part could have a localizing, a part where it weakens and form a localized shear zone, but that would be from grain size reduction. Okay, so why actually do I put these things about having a fabric transition here and a grain size reduction? Well, there's two reasons. One is because when you look at exhumed rocks and you study them, you find those two things happening in ductile shear zone. And number two, because mechanically they can have a very strong effect. So let me show you a few rock pictures there. I haven't seen many rock pictures yet, so there we go. Here's a comparison of a granite in Brittany in France and a highly deformed one in the South American shear zone nearby. This is supposed to be the same material, but here highly deformed in the shear zone. And by studying them, we see some difference. Of course, you have different minerals here, the black and the yellow and all these things, whatever. Their name doesn't really matter much today. And what you find is that when you're looking from here to there, first off, these regions in here, you have a much smaller grain size. Just look at the speckles on this. They're much smaller here than they were there. And the second is that you form these layers of the black stuff, which turns out to be the weaker minerals anyway. That seems to be fairly unconnected throughout the process. So we have evidence for reduction in grain size and formation of an interconnected network. We've been able to evaluate the importance of these various phenomena. For example, you compare the strength of an aggregate that is deforming when you have a structure like this with dispersed particles and one in which instead you have layers of different material. This is much weaker. It's not forever. That the strength here will be controlled by the strong phase, here by the weak phase. But what we've shown recently is that if this weak phase happened to have a very highly nonlinear rheology, you could have increase in the deformation rate. So you start with the same stress and you change the fabric, your strain rate could increase by many orders of magnitudes, way too many to mention actually. It's kind of scary when you do the calculation. But basically you could have a very weak rock here if the material here is highly nonlinear, and micas, ferrosilicates, the stuff that are present in these bands are extremely nonlinear. So this could mean that if you have this type of minerals present, form a fabric, boom, you basically have some really sliding, very weak material there. Grain size reduction is observed in mantle rocks. Here is an oceanic peridotites that have been dredged from the seafloor along the Chaire fracture zone. And you see again this kind of interconnection things. It turns out that for the mantle rheology, the rheology are probably not nonlinear enough to make a big effect just from the layering itself. But what you can see is an intense reduction of grain size. The original grain size is probably of the order of a few millimeters, like we see in those remnant grains there, and seen in undeformed peridotites in other places. But inside these deformation bands, you look and you zoom in and you find just a few microns on grain size. So there's been an intense grain size reduction. And it turns out that if you have the right deformation regime, that can also produce the localization. Just giving you an example of some of the calculations we've done of these processes. So this is a work that really was led by Frédéric Guidon in this case. And what is done is to just take a pile of synthetic rocks and just shear them uniformly with some evolution law for the fabric or the grain size and things like this, and see whether you form a localized shear zones, like in this case here, you have a high strain, a low viscosity band, or you don't, like in this case where the deformation is much more uniform and the strength is much more uniform. And basically he was able to map out the conditions for which you have this and for which you don't. And so shear zones happen from different processes. This is for crustal type of rheology, and really the key there was to have formation of this interconnection of a weak phase, if that weak phase happens to be ferrosilicates. And here for the mantle type of rheology, we got these shear zones formed if you have if you enter a certain deformation regime called the dislocation accommodated grade boundary sliding, this GBS, excuse me for the shortcut there, and right, and so you can do this. And the key though, the fun thing that we noticed that in both cases, and didn't have to happen like this, but in both cases you form shear zone when you're relatively low temperature and you don't when you're at higher temperature. The reason being that geophysics here break down, and actually their strength is about the same as the surrounding rocks eventually, so you don't have much contrast in strength between the phases there, so you don't really have a weak mineral anymore. And here simply because when you are high enough temperature, the way that the deformation regime works, you avoid this magical regime of this GBS, and we can understand why it doesn't do this. Again, I don't have much time to present the details, but that's still our conclusion. So if you're looking at the Earth, we end up with this picture where you have weakening due to the brittle development of fabric in brittle regime in the upper crust, weakening in the mid crust due to the development of layers, nothing we could find in the deep crust, and weakening. If the top of the mantle is cold enough, you will have weakening in the subcontinental mantle due to this grain size reduction, and nothing we could identify to greater depth. So this is the amount of weakening we expect at various depths of the Earth. The idea here that the central part of the talk is to develop a strain-dependent strength envelope. So this is what I'm showing here. Here's the kind of classical view from just taking the rheology from the lab, and you got this kind of profile of the strength, so very much similar to what actually we saw in the previous talk as well, just zooming into the crust and the upper mantle. As you increase the strain and you have this transition, you decrease the stress here, here, and there. You don't in the middle. Overall, you're weaker, so you go faster, etc. The point is that eventually you have a transition to this regime where you have a high resistance in the lower crust and reduction of the strength up and down, but it's also accompanied with an increase in the strain rate. And so you go from a material which deforms fairly uniformly here. As you have this strain evolution, you end up with a localized shear zones. At least that is conceptually what we're looking at. So, okay. So this type of envelope, this type of concept was mostly for continental lithosphere. Now the idea is what's going on when you take this and you move it somewhere else. I'm actually going to skip the oceanic lithosphere and go right away to Venus. So these same processes could happen on Venus, but do they? Well, the mantle, you would have to have a cold enough mantle, essentially, to have this location at accommodated grain boundary sliding. And so that will happen if you have a low heat flux, like geothermal, low heat flux, or a thin crust, or a thin crust. So the heat flux on Venus, is thought to be lower than on Earth, to be something like 1510 Kelvin per kilometer, for example. Those are kind of ballpark numbers. And that would tell you that this GBS creep could happen if the crust is thinner than 22 kilometers in this case, or 30 kilometers in this case. Now, as we already heard yesterday, there's some information, although it's not great necessarily, about the crust of Venus. This is just taken from a recent paper by Peter James and co-workers. And what you see is that in a lot of Venus, the crust is thinner than this magical number of 20 or 30 kilometers. So you should have the potential for localization in the uppermost mantle. It doesn't happen in crustal plateau, interestingly enough. So it may be that one of the differences in the tectonics there is that this crustal plateau don't have possibility of localizing in the mantle. As for the crust, of course, the thing we know from the crust has high surface temperature, no water at the surface. We already know at depth, we don't really know what's going on at depth, but close to the surface, and that's where the crust is, you probably are dry. So these weak minerals are not something we expect to find in the Venusian crust because they happen, all of them, to be hydrated. So this brittle weakening, the fabric weakenings probably are not quite as important as on Venus as they are on Earth. So we end up with a picture where the crust doesn't localize easily. The mantle could, but the mantle is kind of just a small band surrounded by those regions that don't want to localize, that don't want to have localized shear zones. So maybe this is one of the reasons why Venus does not seem to be able to do large-scale plate tectonics, large-scale plate boundaries. Basically, the crust cannot weaken, the lithosphere cannot weaken as much as it does on Earth, even for the continents. Well, but I did tell you there's some places that look very much Earth-like on Venus, like the rift that I showed earlier. Well, so that puzzles me. But there, of course, always a way to argue your way around anything that you find in planetary science. So, for example, one of the things to realize, of course, is that this strength profile are different whether you're in compression or extension. And extension tends to make you more brittle or brittle to greater depth. So comparing here the same conditions here, the strength envelope for compression, for extension, you find a larger importance of the brittle regime and much less in terms of the crust there, of this kind of ductile crust at depth. So it is possible that, the formation of layering may not be as efficient on Venus than it is on Earth, but maybe it does a little bit anyway, and that's sufficient when you are dominated by when the lithosphere is dominated by that brittle regime, which would be the case in extension, but not in compression. It's also true that when you're rifting, when you're upwelling things underneath the rift, you can melt, and this melt could produce some additional weakening. It's also true that you have some stress focusing effect due to the thinning of the lithosphere as you are rifting it and things like this, which basically means that, generally speaking, localization should be easier in extension. So it's kind of neat, in fact, that Venus is Earth-like in some rifting environments, but not in compression, because this may be just at the margins when we are able to really test these ideas so that it works in one regime and not in the other. Moving on to Mars very quickly. So the same type of stories, the mantle could localize if you have low enough heat flux or thin enough crust. And basically, in the lowlands, where we think the crust is about 30 kilometers thick, you would need a heat flux of 100 milliwatts per square meter. In the highlands, where the crust is thicker, you need a heat flux kind of half that much. And on Mars, we think at least that the heat flux has changed over time. There's some modeling aspect of it, but the boxes you see on this diagram are actual inferences of heat flux from various geological and geodynamical inversions, from wavelengths of flexure to spacing of tectonic features, etc. And what you can see is 100 milliwatts per square meter is present everywhere. So basically the lowlands, the crust is always thin enough that you should have a localizing upper mantle. The highlands, that would be the case not early on, but only in the recent part. Of course, the activity has stopped pretty much in the highlands since that time. So it's a little bit like maybe if we were to restart Mars today, it could localize because it's cold enough, but at that time, the highlands were not. It's not really clear what's going on so much. The crust, well, I'm not going to play a game with water there. Water is probably present in the crust, so you could have any of this weakening. You have phyllosilicates, we know them at the surface. There's no reason to think that they are at depth. However, the composition of the crust is more mafic than what we have on Earth. And it turns out that most of the micas and the phyllosilicates we will be using on Earth are coming from the decomposition of felsic rocks. So bear with me for putting a bit of mineralogy there, but basically we wouldn't form the right type of phyllosilicates on Mars than we do on Earth. I have 3 minutes, and here's the most complicating diagram of it ever. Summarizing essentially all that I said there, for each planet what you're looking at is the surface is here and you're going to greater and greater depth. And what happens horizontally is just changing some characteristics, like the heat flux on the continents on Earth, the time for Mars, heat flux on Venus, etc. And I do it for two depth of the crust, kind of a thin crust and a deep crust, where we have on Earth, on Mars, on Venus. And I highlight the conditions where you have brittle and dislocation of accumulated grain boundary sliding and fabric. So basically those highlighted regions are the ones where localization is thought to be possible. And what we can see is that Mars actually looks a lot like the continents, and Venus looks like nothing else in that it could have deep localization but not connected to the surface in any possible ways. So maybe this is why Venus doesn't do the things we see on Earth, because in fact you have this decoupling layer at the surface. At least we can't observe what is at the surface. There were some very ancient talks about two-level tectonics on Venus, which has been kind of thrown out the window. But this is kind of what we start to look back at in these stories. Maybe buried plate tectonic stuff which doesn't have an expression at the surface. But let's not go there too much yet. So why Mars doesn't do what it does? Well, okay, let me move on very quickly to the idea of driving forces. So this just was looking at the strength envelope. If you have deformation, what's going to happen to the strength? But it doesn't address the question, do you have deformation to start with? Because for that you need to look at the driving forces. Earth, we think that most of the forces, although we heard differently today, the tectonics is mostly driven by faraway forces, whereas on an environment like Venus, where you have no plate tectonic currently, so if you don't have plate tectonics, you mostly have stress from the base of the lithosphere. And it turns out that these stresses are very inefficient at driving tectonics, simply due to the fact that you would have essentially a pure shear environment here, constant stress, and that stress is limited by what you have in convective regime, typically smaller than what you need to produce rifting at the surface. Skip the actual number here to tell you that one of the key, though, that may produce tectonics in some environments may be actually buoyancy, what I call buoyancy-driven tectonics. Some of the diagram that I end up drawing for both Venus and the East African rift is that, in fact, you may have influence of an upwelling in the mantle that is kind of lifting the crust and stretching it more than really the plates pulling apart on the crust. So this may be actually why the East African rift and the Van Chasma on Venus look a lot alike. And I want to point out a recent paper by Ray et al., published just a couple of weeks ago, I think, where they show for the Earth is Archean the influence of some buoyant cratonic continental root, essentially, that would be spreading and generating some short-lived localized subduction here. So these buoyancy forces from both residual here on the continents and from mantle plumes may be producing local tectonics, but don't seem to be able to generate this and put it all the way to the scale of the planet unless you have this intense localization that I mentioned, which may not have been the case in the early Earth and may not be the case today on Venus. And I think I will just stop here. Thank you.